Two, welcome to the last lesson of lesson six of topic six, lesson 6-7. We're going to talk about geometric series and sequences. Here's our essential question for the day. Let's get right into it. All right, so here we go. We have a table here. We want to know if this is a geometric sequence. If it is a geometric sequence, then the common ratio between each one of these values is going to be the same. What I mean by that is, so this is a sequence with, we're going to call this a sub 1. We're going to call this a sub 2. This one's a sub 3, a sub 4, and a sub 5. And this is what we want to know. Is it true that a sub 2 divided by a sub 1 is not the same thing as a sub 3 divided by a sub 2, right? In other words, I want to know is if I take a term and I divide it by the previous term, so I get the same thing every time. So is it true that 12 divided by 4 is the same as 36, right? A sub 3 divided by 12. And I get 3 equals 3. Looks good. I'm going to check one more. Is it also true that 108 divided by 36, is that equal to 3? Put that in your calculator or do it in your head, and you'll find out that indeed it is equal to 3, which means that this is a geometric sequence. And what we have just found is R. R is our common ratio. Another term that we've just picked out is that a sub 1 is our first term. And we'll find that we can actually refer to a sub n as any nth term of the sequence. All right, so we have determined in this case that R, our common ratio, is equal to 3. So this question is asking us to write a recursive definition. I'm actually going to go ahead and write two things: the recursive definition and the explicit definition. All right, so let's talk about these definitions. So first of all, we have the recursive definition. Well, it's like this. A sub n is equal to a sub 1. We'll put n equals 1 here. And here, this will be R times a sub n minus 1 for any n greater than 1. Our explicit definition is that a sub n is equal to a sub 1 times r to the n minus 1 power. All right, so we know what a sub 1 and r are in here. We have that a sub 1 is 4. And we know that r is 3. Let's go ahead and plug those in to these. So we have that a sub n is equal to a sub 1, we said it's 4. For n equals 1. And r is 3, so this is 3 to the times a to the n minus sub n minus 1 for all n greater than 1. Over here, our explicit formula for this is going to be a sub n equals 4 times r to the n minus 1 power. All right, let's try another one. Here we go. We want to know, is this a geometric sequence? And if so, we're going to write both, actually, the recursive and explicit definitions. So first of all, let's see if we have a common ratio here. So is 9.6 divided by 12 the same thing as 7.68 divided by 9.6? And I'm going to go even further. Let's check 3 of these. Let's see if 6.144 divided by 7.68. Let's see if these are all the same. So I will put them into my handy dandy calculator. If it 9.6 divided by 12 is 0.8. I put this ratio in, and I also get 0.8. I put the ratio of 6.144 divided by 7.68 in my calculator, and I find that that is also 0.8. What does that tell us? It tells us, one, that it is a geometric sequence, and it tells me also that my common ratio R is 0.8. So we know what R is. We know that a sub 1 is 12. And so our recursive definition is going to look like this. We have a sub n is equal to, remember, a sub 1 goes right here, 12. And that's for n equal to 1. And over here we have 0.8 times a sub n minus 1 for n greater than. For our explicit definition, we have that a sub n is equal to a sub 1 times r, which is 0.8. That's going to go to the n minus 1 power. All right, let's do one more before we move on. So, what do we think our common ratio R is here, right? So 20 divided by 4 is -5. Negative 100 divided by 20 is -5. 500 divided by -100 is -5. So I'm going to say that R is equal to -5. A sub 1, our first term, is -4. So that means that our recursive definition is going to be -4 for x greater than 1. N, my bad. For n equal to 1. And -5 times a to the n, a sub n minus 1 for all n greater than 1. Our explicit definition is going to be a sub n equals -4 times -5, right, r to the n minus 1 power. All right, let's get into something a little different real quick. Here we go. All right, so if we're given this recursive definition, let's write the explicit definition for it. So here, the information that I'm going to pick out of this is that that is a sub 1. So a sub 1 is equal to 5. And that r is right there. R is equal to 1/2. So if I was going to write the explicit definition, it would be a sub 1 equals, sorry, a sub n equals a sub 1 times 1/2 to the n minus 1 power, just like that. All right, let's go ahead and do a problem with this. All right, so we've got this phone tree example. So one person calls a certain number of people, and then those people call the same number of people, and so on. We find out that on the 5th round of calls, 243 people were called. So what they're telling us is that a sub 5, The fifth one is 243. Okay. We have a formula that tells us that a sub n is equal to a sub 1 times r to the n minus 1. Well, we know that it starts with one person, yeah? So what we're being told is that n, also what this says is that n is equal to 5. So a sub 5, 243, is equal to a sub 1. All we said is 1 because we're starting with one person. And we don't know what r is. I'd like to know what r is. We do know that n is 5. So we're going to substitute all that in here. And we're going to solve this thing for r. So we get that 243 is equal to r, right? The 1 multiplying is not going to change it. So r to the 5 minus 1 over 4 power. In order to solve this, I need to take the fourth root of both sides. And that's going to tell me that r is equal to 3. So the number of people called in each round, there are 3 people called in each round, just like the picture. All right, so let's do another one of these that is a word problem. So we've got the growth of bacteria in an experiment. The first day of the experiment, there were 9 bacteria. So what does that mean? That means that a sub 1 is 9. On the 10th day, so a sub 10, there were 3 to the 20th power bacteria in the dish. How many bacteria were in the dish on the 7th day? So I'm going to get out my explicit formula here. It tells us that this is a sub 1 times r to the n minus 1. And we know a sub 10 is 3 to the 20th power. Tells us that a sub 1 is 9. We don't know r, but we do know that n, right? N is 10. So this is 10 minus 1 here. I'm going to go ahead and do 2 things at once when I solve this. I'm going to go ahead and divide 3 to the 20th power by 9. And I get, I believe that is 387,420,489 equals r, and now 10 minus 1 to the 9th power. So I'll take that, and I will, I'm going to take the 9th root of both sides. And let's see what that is. Oh, interesting. So the 9th root of that is 9. So we get that r is equal to 9. But they want to know how many were in the dish on the 7th day of the experiment. So now I can go back to my recursive formula, right? We want to know on the 7th day, we know that a sub 1 is 9. Now we know r is 9. And now instead of n minus 1, right, we're going 7 minus 1. And we'll just get an answer for this. So this is 9 times 9 to the 6th, also 9 to the 7th power. So you get 4,782,969 bacteria. All right, so the next thing we're going to talk about is going to be geometric series. So that is where we are adding a term that's geometric, right? We're taking a bunch of geometric terms, and we're adding them up and finding a sum of geometric terms. So interestingly enough, right, I'm gonna write this thing out for you. I'm gonna use some different notation as well. This is sigma. What sigma does is it adds a bunch of stuff, and it tells us where to start adding. So what it does is it says, hey, add all the way up to n, okay, n terms. This one tells you which term to start with, okay? And for our geometric series, we're going to have this is the explicit formula for a geometric series, yeah? The way this expands is like this, okay? This is a sub 1 times r to the 1 minus 1 plus a sub 1 times r to the 2 minus 1, right? You can see that this value of m keeps changing with each term, it increases, okay? So this says go up to n terms, start with 1, and then go up. M is going to go up one number every term, right? So this would be plus a sub 1 r to the 3 minus 1 plus, and it goes all the way up to a sub 1 r. Okay, that being this n tells you where to stop. This actually, quite fortunately, you don't have to add them all, right? You don't have to write it all up and add it all. There's actually a formula that works for this. And it tells me that the sum of all of these is equal to a sub 1 times 1 minus r to the n power divided by 1 minus r. But I can do you even better than that. I'm going to show you how to calculate these with your calculator. Just about instantaneous, all right? All right, so let's just go ahead and apply this now. This is quite theoretical. Let's go ahead and do this with some real numbers, you know what I'm saying? And so we're going to write the expanded form of the series, and then we are going to calculate the sum. I'm going to show you how to calculate it longhand, and then I'll show you how to get your calculator to do this quite quickly. So if we're going to expand this, this is going to be equal to 3 times 2/3 to the 1 minus 1, right? Plus 3 times 2/3 to the 2 minus 1. And then you can go like 1, 2, skip a few, you know what I'm saying? And we go all the way to the last one. This is going to be 3 times 2/3 to the 7 minus 1 power. Now we have a handy dandy formula that tells us that this is the same as 3 times 1 minus 2/3 to the 7th power, all divided by 1 minus 2/3. Now, at this point in time, you can put that exact thing into your calculator, and it's going to spit out an answer. Yeah? But I want to show you something neat. that you can do with your calculator. All right, so let's get out our handy dandy calculator. And I'm going to show you how to input this. So you're going to hit math, and then you're going to scroll down and you'll see that there is a summation. You're going to hit enter on that, and you're going to enter all this stuff. I am going to recommend that you call this one x equals 1. We were going up to 7, I believe. Yep. Going all the way up to 7. And this was 3 times 2/3. That is getting raised to the x minus 1 power. I think that all looks right. We'll double check. 3 2/3, x minus 1, 7 looks good. And then we're going to hit enter. We get approximately 8.473. Put that up there. This is approximate since we have rounded. And there you go. So let's go ahead and move on and try something new. Let's find the number of terms in a geometric series. My bad. Okay. So what information do we have from here? What do we know? We know that a sub 1 is equal to 200. Yeah. Our common ratio, R, looks like 3 divided by 2. We check them all out, and we're just going to actually we'll put it as 1.5. We can put it as 3 halves if you want. I think we're going to leave it like that. And then we also know that the last term, our nth term, a sub n, is equal to 7,688. So there's our information. So we know that a sub n is equal to a sub 1 times r to the n minus 1 power. That is our explicit formula for a geometric sequence. But this series is just going in that same sequence. We're not actually adding anything. It's just showing you what we would be adding, right? So I'm going to plug that stuff in. 7,688. 688.7 equals 200. Just plugging stuff in. We know that R is 1.5. And there we go. We need to know what N is, yeah? The only missing piece of information. What is N? We're going to solve this for N. So my first step is going to be to divide both sides by 200. If I divide 7,688.7 by 200, I get exactly 38.4435. That is 1.5 to the n minus 1. I'm going to do something weird and take log base 1.5 of both sides. I do that because it helps me eliminate a step. Okay?
And we have the log base thing on our log base function. It's not just a thing, it's called the function on our calculators. The reason why I do that so that I can pull that n minus 1 out, and it'll be there all by itself. All right, so we're running out of room, so let's move this over here and continue. Okay. So I've got log base 1.5 of 38.4435 equals n minus 1, right? I can pull the n minus 1 to the front. And then remember, log base 1.5 of 1.5 is 1. That's why I chose log base 1.5. Because I want that thing to go away, right? And I'll say, right, this is because log base 1.5 of 1.5 equals 1. So it basically goes away. I only have one more step to do. Log base 1.5, 38.4435 plus 1, right? I just got to add 1 to both sides. Now we can just put that. So this is an exact answer, right? But that's not good because what we really need is like a digit for what n is, right? Which term is it? It's either, you know what I mean? So we'll put this into our handy dandy calculator. I'm going to get out my log base. Is that right? 38.4435. Well, we got to add 1, right? And it looks to be the 10th term. So this is 10, basically. So we'll say that it is approximately the 10th term. All right. All right, sweet. Let's try another one. Get rid of that. All right. Ooh. The sum of the geometric series is 11,718. The first term of the series is 3, and its common ratio is 5. How many terms are in the series? So what they're asking us to do is use a different formula, right? They want us to use the formula that says that we have some sum of some geometric series is equal to a sub 1 times 1 minus r to the n power divided by 1 minus r. Okay, we're going to use that. All right, so what do we know? We know that as sub n, the sum is equal to 11,718. We know that a sub 1, the first term, is equal to 3. And we know that our common ratio r is equal to 5. So let's plug that stuff in, see what's missing, and solve for it. It's going to be n. All right, so what do we got then? 11,718 is equal to 3 times 1 minus 5 to the n power. We don't know that. We don't know what it is. And then we've got, this is 1 minus 5. Okay, let's solve this thing. I'm going to move this over here so that we don't run out of room. Because this is going to be a couple steps. 3 times 1 minus 5 to the n power over 4, negative 4. And so now we need to multiply both sides by negative 4 to get rid of the negative 4 over there in my denominator. We're going to get negative 46,872 over here. We get 3 times 1 minus 5 to the n power. We're going to have to divide both sides by 3 to get rid of that 3. And I get 15,624. That is what negative 46,872 divided by 3 is. And then I don't need these parentheses anymore because the 3 is gone. Now we are going to have to subtract 1 from both sides. So subtracting 1 from this negative number is going to make it more negative. I very much dislike the negative sign sitting out from there, so I'm going to divide both sides by negative 1. Just changing the sign of everything, I'm going to change everything to positive. And now I'm going to take log base 5 of both sides. And I'm having a good feeling that this is going to work out really nicely. Being that this ends in a digit. It ends in 25. It ends in 625. These are all powers of 5, so it's making me feel nice. All right. So let's go ahead and put log base 5 of 15,625 in here. $15,625. Ooh, 6. Nice. So I guess that's 5 to the 6th power. So we get 6 equals n. All right, because we get log base 5 of 5. Kind of skip the step where I pulled the n out. Not kind of. All right, so let's rock out another one of these. We like scientists. They do science and rocket surgery, brain science. What do we know? We know that a sub 1 is 6. What is r? R is 2, right? 12 divided by 6 is 2. 24 divided by 12 is 2. Looks like r is 2, right? What else do we know? We know that a sub n, our last term, is equal to 3,072. Sweet. So we'll plug it into our handy-dandy formula. That's a sub n. We know that a is 6. A sub 1 is 6. R, it's the pirate's favorite variable, is 2 to the n minus 1. they're like, Blackbeard, what should we name the common ratio? And he was like, R. I don't care. Let's go ahead and solve this. The first thing I'm going to do is divide both sides by 6. So 3,072 divided by 6 turns out to be 512. And I have 2 to the n minus 1. I'm going to go ahead and take log base 2 of both sides to save a step. That's going to, let's actually go ahead and take log base 2 of 512. It turns out that is 9. And then we'll have the n minus 1 pulled out here. Right? I skipped this step in the last one. I'm not going to do it this time. So now we have 9 equals n minus 1 because log base 2 of 2 is 1. And then all I need to do is add 1 to both sides and I get that n is equal to 10. All right, so that is the last example from 6.7. Hey, Algebra 2, thanks so much for watching. But I was. Hey, Algebra 2, thanks so much for watching. Hope you're having a beautiful day, and if you're not, hope it gets better. Smile at someone. Sometimes that helps.